Okay. Hi everyone. Thank you for joining the seminar today. Today we have an excellent guest from the University of Cambridge, Hayley Macpherson, who used to be at Monash. I would like Paul to introduce her.
Of course you do. Gives me great pleasure to introduce Hayley Macpherson. Sorry, flustered now. Hayley did her undergraduate here, graduating with her honours degree with Daniel and I in 2016. Is that right? 2015. And then PhD, which finished in 2019. I know that one. PhD finished in 2019, was awarded everything under the sun for that PhD, including the university's Molly Holman Award for the best PhD in science, the Charlotte Heisler Award at the ASA, the Astronomical Society of Australia, and I think there was one more, the physics one, Robert Street Doctoral Prize as well. So that was an award-winning thesis, got a fellowship at University of Cambridge, so Herschel Smith Fellowship, which is just finishing up. Are we allowed to say what's next?
Yep.
And is moving over to the University of Chicago on a Einstein/Hubble Fellowship very, very shortly. So it's been a continuing meteoric rise, and she's going to tell us about some of her research today. Take it away.
No pressure.
Yeah.
Yeah, thanks so much. Super cool to be back in this room again, where I did all my PhD defenses and all that kind of stuff. So it's pretty awesome to be back, and I'm really excited to tell you about this work at this archive number if you're interested in reading more, which I did with my collaborator Heinesen, who's a postdoc in Lyon. And in this work, we were interested in looking into the effects of low-redshift cosmological anisotropy and its potential effects on our cosmological observations. And I will explain what that means. A key focus of cosmology is really to find a theoretical model which provides the best fit to our cosmological observations. And those observations really span almost the entire history of the universe, so from the far left to the far right in this diagram. We can learn about the very early state of the universe from our observations of the cosmic microwave background, or the CMB, on the far left, which is the first light that was able to freely travel through the universe after the Big Bang, once it became opaque to radiation. And sorry, transparent to radiation, not opaque. And so measuring that radiation today allows us to learn a lot about the very, very early state of the universe very soon after its birth. And we learn about the late universe using our observations of galaxies in the late universe around us today, in particular this cosmic web, which we call the large-scale structure. So galaxies around us form this web of clusters and filaments and void regions. And what we want is for our theoretical model to marry these two together to give us a consistent picture about the full evolution of the universe. And ideally, we would also, within this theoretical model, we would also understand the parameters of this model to gain some physical understanding of how the universe has evolved over time. So cosmologists have done a reasonably good job at this, that's understating, but at building what is now our standard cosmological model, known as the lambda-cold dark matter or lambda CDM model. And this model is named after the main constituents of the universe that we infer from our observations. And so lambda represents our cosmological constant, which is our best theoretical description for dark energy, which again, we don't really know what it is, but it's some mysterious fluid which is forcing the expansion of the universe to accelerate at late times. The CDM, or cold dark matter, just means, well, cold or non-relativistic, some kind of matter which we don't quite know what it is, but we know it must exist from our observations. And so this dark energy makes up 70% of the energy density of the universe. Our dark matter makes up most of the matter in the universe, or 24% total, and only about 4% of the universe is all regular atomic matter that we see all around us. And so this model is based on Einstein's theory of general relativity, specifically under the assumptions of a homogeneous and isotropic space-time metric. So all this means is that our space is the same regardless of where we're located, and it's isotropic, so it's the same regardless of which direction we're in.
Yeah.
And so under these assumptions, we arrive at the Friedmann-Lemaitre-Robertson-Walker, or FLRW class of models within general relativity, which I'll say a little bit more on the next slide. In reality, what we do is we typically assume that the universe is well described by this model on average on large scales in the universe. So it's typically used as kind of a zero-order description for the dynamics and expansion of the universe. And this lambda CDM model has been extremely successful in explaining almost all of our cosmological observations to date in a surprisingly simple framework. I mean, this is oversimplifying it a bit, but it's really not that much more complicated than this. But as our observations get more and more precise, we are starting to see some tensions or disagreements between predictions of the lambda CDM model and our cosmological observations. And the one that we've probably all heard about a lot by now is the Hubble tension. And so this is a mismatch between our theoretical prediction based on lambda CDM of the expansion rate at redshift 0 or around us, so this is H naught parameter, and what our kind of like local universe measurements tell us. So basically disagreement between theory and observation. And so Edwin Hubble was one of the first people to measure the expansion of the universe. And so this plot here is showing his plot from 1929, where we're looking at the distance versus redshift of a set of extragalactic nebulae, and the straight line going through them tells us that the further away we look, the faster things are moving, which tells us that the universe is expanding. And basically the slope of this line tells us just how fast the universe is expanding. And so Hubble's early measurement gave us something around 500 kilometers per second per megaparsec, which just means that for every extra megaparsec we go away from us,
between the purple and the green filament.
500 kilometers per second away.
That's good.
So since 1929, even since then, our observations have gotten more precise. So here we're looking at measurements of the value of the stational parameter, how fast the universe is expanding from redshift 0 as a function of publication date.
You prefer
And
this
so
one?
Hubble's measurement is somewhere around here. So we can see that nowadays we've somewhat converged on a value that is not 500, but is a bit closer to 70 kilometers per second per megaparsec. But even within this is a very old plot, obviously, but even within this, two of the main ways that we measure this parameter are in disagreement with one another. And one of them is to do with these early universe measurements of the CMB that I mentioned before. So this on the left is showing us an all-sky map, the mole-wide projection of the CMB radiation that we measure, where the red spots are hot and the blue spots are cold. The difference between them is about one part in a million or so. So they're very, very tiny fluctuations that we measure across the sky. And so very broadly speaking, what we do to measure these or predict the expansion rate today is we find the best fit lambda CDM model that describes this radiation, and then we can extrapolate that model to low redshift to give us a prediction of the expansion at late times based on that theoretical model. Another way we can do it is to essentially measure the expansion rate near us and see if it agrees with this theoretical prediction. And so one of many ways that we can do this is using type 1H supernovae, one of these shown in its plot, outshining its host in this picture, outshining its host galaxy. This is just a particular type of exploding star, which is very useful for measuring distances in cosmology. We can calibrate these using Cepheid variable stars. I won't go into details about this. It doesn't really matter. The point is that we can make a model-independent inference of how the universe is actually expanding near us today, and compare this to the theoretical prediction and see if they agree. I've put quotations around this model independent, which will hopefully make sense in a few slides' time. By the way, I meant to say earlier on, feel free to interrupt me with questions at any point. I want to make sure that we're kind of all following along. So if anything I say doesn't make sense, please don't hesitate to ask. And so now what we're going to do is look at these, what these two different probes have given us for H0 as a function of time, and see how they've come to disagree with one another. So this is the same plot that I showed a few slides ago. We're just looking at measurements of H0 as a function of publication year. We're essentially just carrying on from the previous plot from 2000 down to around about today. And so these red points here are showing the H0 measurements from the early universe, or measurements of the CMB. And the blue points are showing our late universe measurements, and specifically using supernovae. We can see that as the error bars have gotten smaller and smaller, these two values have diverged from one another. And basically, I just tacked on these most recent measurements here on the end. And the problem is that they're quite a few sigma away from one another. And so this point here is telling us what our lambda CDM model predicts, what the expansion rate should be today. And this point here is showing us what we measure. And so this is obviously quite a big problem in cosmology. And there are lots and lots and lots of people working to try and describe this. This is just one of these interesting tensions. There are a few others that I won't go into detail. But in addition to these tensions, there is, of course, the 95% of the energy density of the universe, which we still don't have a physical explanation for. And so I think both of these are motivation enough to explore alternatives to the Lemaitre CDM model. And there are lots of people working in many different areas. Some people are interested in looking at new exotic physics beyond the Lemaitre CDM model, potentially modifying Einstein's theory of general relativity. But what I'm most interested in looking at, and what my work is kind of centered around, is investigating the effect of existing physics that we know is there, but is neglected within the standard model. And in particular, this goes back to these assumptions of homogeneous and isotropic spacetime. And so, as I said earlier, making these assumptions of homogeneity and isotropy implies that the Friedmann-Lemaitre-Robertson-Walker, or FLRW metric, describes distances in the universe. And the metric just tells us about the geometry of our spacetime. And so let me just walk through this. This ds here tells us the infinitesimal distance between 2 points in a given spacetime. That's all that ds is telling us. And we can write this in terms of our metric tensor, g nu, and our distance in each of our spatial and time conventions here. And under these assumptions of homogeneity and isotropy, our distances are described by this line element here. And the point I want you to take away from this is that our distances, so our ds, are described entirely by one function of time. And so that's what we call the scale factor in cosmology. And so this is the function that we use to describe distance everywhere in the universe within FLRW. And this constant k here just describes the overall geometry of our universe, the overall curvature. So this is whether, in a spatial sense, our universe looks like a sphere or a saddle or is flat. And so, as I said before, we don't really assume that the universe is perfectly FLRW everywhere. We typically use this as a background or a zeroth order description for the dynamics of the universe. And in particular, this depends on the specific problem that we're interested in talking about. So this might be if we're interested in looking at really large scale cosmological dynamics, we will typically use FLRW as a background with small perturbations on top to describe kind of like large cosmological perturbations. Or it's also used if we're interested in small scale nonlinear dynamics as a background expansion within our Newtonian cosmological simulation. So these are all the regular n-body simulations that you're used to seeing in cosmology. We'll have our background expansion as the FLRW with the particle dynamics added on top using Newtonian gravity. And so this is where this model enters throughout cosmology. And so, yeah, most of cosmology today relies on the assumption of this metric as a background. And just for example, our measurements of the local Hubble constant, which I showed you before, the detection of the baryon acoustic oscillation feature, and the analysis of the CMB all explicitly assume an FLRW geometry. And so now we're just going to switch gears and just focus on our low redshift or local measurements of the universe. And so in particular, from now on, I'm going to talk about low redshift observations of objects like supernovae. So this plot here is showing each point here is an observation of a supernova. So we've essentially got redshift and then magnitude on the y-axis here. And again, just like Hubble's plot, this straight line tells us space is expanding, which is good news. So the further away things are, the dimmer they are. And so this is what we measure in our supernova. We measure their redshift and their magnitude. And we're interested in using these objects to learn about the cosmology of the universe, or how the universe is expanding. And in order to do that, in order to extract any cosmological information from this line, we need to parameterize it. So we need to write down the line in terms of our cosmological parameters, and that is where the FLRW model comes in. Yep.
Why is the x-axis so green?
This.
What is that?
That is like, well, this is like some translation of the redshift into distances. Don't worry about that. So complicated. Redshift, which is this one here. It's just showing you the redshift. And so the way we parameterize that line, as I said, is using FLRW. And so one way to do this is called cosmography. And in cosmography, what we do is we write down the luminosity distance, which is simply related to the magnitude of these objects, in a Taylor series expansion in the redshift. And so write like this, usually truncated in a third order in redshift. And then using the FLRW metric, we can derive each of these coefficients in first, second, and third order, which then look like this. And these coefficients are written in terms of the familiar cosmological parameters of the Hubble, deceleration, jerk, and curvature. And so the Hubble parameter is what I was talking about, this tension between our measurements. And they're all related to different derivatives of this scale factor, which, as I said before, describes the scales of the universe. And so this Hubble is just the first time derivative, so that's telling us how space is expanding or how our scales are changing over time. Our deceleration parameter is related to the second derivative of the scales in the universe. This tells us how length scales are accelerating over time. Jerk is the third derivative, and the curvature is related to this constant K, which I introduced before, which tells us about the spatial curvature of our FLRW universe. And so in getting here, we've explicitly assumed an FLRW metric, but we haven't assumed anything about the field equation. So we haven't assumed anything about how our scale factor A of t evolves. So it could have any kind of expansion history. And this is exactly why cosmography is a very attractive method, and it's used a lot in low redshift analysis, because you can maintain this kind of generality in your constraints. And you can constrain some of these cosmological parameters without a priori assuming, for example, a particular curvature or a particular amount of dark energy or dark matter. And so this is exactly the framework that's used to measure the local Hubble parameter. And in fact, if I go back to this complicated x-axis, you'll see that's the expression that it is down here. And so this, using the FLRW metric, gives us this very simple relation for the luminosity distance as a function of redshift. And historically, this might have been justified because of the limited amount of cosmological data. And so in order to be able to extract any kind of cosmological information, we need to make quite a lot of simplifying assumptions. But we're getting a lot more data these days, and both the increasing sky volume and the pure amount of data that we're getting means that we will eventually be able to remove some of these assumptions and hopefully eventually completely remove the assumptions of exact homogeneity and isotropy from these constraints. And so this will allow for truly model independent. So now hopefully you see why I had the model independent quotations for our Hubble parameter constraints. So even outside of the context of the FLRW models. And in particular, my collaborator, Heinesen, derived this same luminosity distance redshift cosmography without making any assumption of a particular metric tensor. And so she really derived the complete generalization of this cosmographic formalism. And so within this formalism, we do have a finite number of degrees of freedom, which means that technically we can use it to constrain parameters. Although when you don't make any assumptions, you have many independent degrees of freedom. And in particular, her formalism has 61. And so we can't, we're going from 4 in FLRW to 61. So we can't quite yet constrain all of those degrees of freedom. And so this is Asta's formalism here. So we've got the same kind of logic. We've done a Taylor series expansion in luminosity distance as a function of redshift. But now you'll notice our 3 coefficients are written in terms of these curly parameters. And so these are the effective Hubble, effective deceleration, effective curvature, and effective jerk parameters. And the reason I'm saying effective for all of them is because they appear in the same place in the Taylor series expansion as their namesakes. For example, the effective Hubble parameter is named that way because it appears in the same place at first order as the FLRW Hubble parameter. But the physical interpretation of these parameters is not so simple once you leave the safety of the FLRW metric. For example, if we look at the effective deceleration parameter and go back to the FLRW case, you notice we have this very simple relation between our deceleration parameter Q and the actual acceleration of length scales in our spacetime. But if we now look at this effective deceleration parameter, so we'll be clearer on the couple of slides' time, this connection is not so clear, and in fact, this Q can actually be negative. Sorry, so in the FLRW case, if we measure a negative Q, this direct relationship tells us that this A double dot must be positive, and therefore our length scales must be accelerating. But in this case, in the effective case, we can actually have a negative value of Q without any actual global acceleration of space-time length scales. And that will make more sense in a few slides' time. Similarly, for the effective curvature, if we look back at the FLRW case, we have this very simple relation between this curvature parameter and the actual spatial curvature of our universe. But now we have a more complicated expression, and this effective curvature does not necessarily directly probe the actual curvature of our universe.
Why is there minus 1 in the effective deceleration? As in is this the same as the one thing? With the disciplines that you double up?
Well, I mean, it's not the same. That's when you take the FLRW limit, it will reduce to this one. But this is just what so all she's done is just kind of derive this general expression and then identified the parameters required to make it look like the FLRW case.
These things are all known. If you know the metric, the true metric of space-time, then you can calculate this.
Exactly, and that's what I'll talk about. But for now, this is for a completely general metric. So you do have like the curvature tensor, but you don't know what that actually looks like. Yeah, but when you do specify an FLRW metric, then it does reduce to the regular FLRW cosmography.
Are the K's in the effective curvature term, are they null vectors?
Yeah, sorry, I meant to say I didn't want to go into details about what everything is, but yes, this is so here in this case, the most general case, all you're talking about is an observer sitting in your universe, co-moving with your fluid flow. And that observer has a ray of light coming towards them. And that ray of light is described by some form momentum k-nu. And so this term that comes into the effective curvature is like your Ritchie lensing of your incoming light ray. And then that's all you've really got. So maybe I can go into a bit more details about it. So this parameter E is the energy of your incoming light ray. And this derivative is how the energy is changing along the line of sight from the observer. And so you're kind of replacing this simplified space-time with just kind of derivatives along the light rate.
Are there any constraints that you're placing on this metric? I mean, is it, you are presumably assuming that it satisfies Einstein's equations, right? But you're saying no, you're not assuming that.
No, there's no assumption of the field equations. Oh, disclaimer again, I didn't write this. The full derivation is in Asta's paper here. So I think one of the minimal assumptions she had to make, just to be able to write the luminosity distance in this Taylor series, you need it to be a monotonic function along your line of sight. And so that places some constraints on like how much structure you can have collapsing, because, for example, if you're looking at a galaxy or something like that, your distance will increase, and then you'll get kind of like a backwards and forwards again. So you'll have like a double value line. And so that's kind of a constraint on the physical universe. But as far as I know, there's no constraints on the metric tensor. I guess you must need it to be smooth to be able to take derivatives and get your curvature tensor, but it's very minimal assumptions. This is really as general as you can get.
Presumably, I mean, to have a luminosity distance that's angle independent, you must assume isotropy and homogeneity.
No, that's another thing I should have stressed, is that these parameters are inhomogeneous and anisotropic, which will be made clearer on the next slide. But so these parameters are really inhomogeneous anisotropic generalizations of the FLRW parameters.
They're along a particular ray.
Yes, exactly. Yeah, that's right. And so each of these parameters, which is also in Asta's paper, can be written as a multipole expansion in this vector EU, which describes which direction the observer is looking. And so the simplest case is the effective Hubble parameter here. And so what we end up with is a monopole term, which is given by this parameter theta, which is just the isotropic expansion around the observer. And so this reduces to the Hubble constant in the FLRW limit, but this depends on the observer's location. So this will be different if your observer is in under density or an over density. But then what you also get are these terms which depend on which direction the observer is looking as well. And so you can think of this as this term encompasses the inhomogeneity in this term, and these terms encompass the anisotropy. Does that make sense? And so what we end up with here in particular is a dipole term in the direction vector, which is given by this vector AU, which is the acceleration of the observer. And so if your observer is moving on a geodesic, this term is 0, and so we're not worried about that. We also end up with a quadrupole term, which is given by the shear tensor. And so this describes the anisotropic expansion of space around the observer. And this is not an arbitrary truncation, this is an exact truncation. So this is all of the contributions of anisotropy to the effective Hubble parameter. So only this dipole and quadrupole. All of the other parameters can be written like this as well, but as we go to higher order, they get a little bit more complicated. And so just quickly, I just want to run through this example of the effective deceleration parameter. And so similarly, we have a monopole term, which is independent of the direction we look. We have a dipole, quadrupole, an octupole, and a 16-pole, and this is where that one truncates. And so if we just for a second focus on the monopole term, so the isotropic term, is given by this expression here. This term, we can notice on the previous slide, I told you theta is the expansion, the local expansion near the observer. So this term, this d theta dt, is the term which tells us how length scales are accelerating near the observer. So this is the one term that survives in the FLRW limit and reduces to our A double dot. And so all of these other terms are due to effects of inhomogeneity and anisotropy. And hopefully now you believe me that this direct relation between a particular value of Q and acceleration of length scales is not so obvious when you include the effects of inhomogeneity and anisotropy. I will just point out that, as I said before, this acceleration vector A mu for geodesic observers, which should be a pretty good approximation for us, will be 0. And so a lot of these terms will drop out, but we still have some contributions which are non-trivial. And in particular, I just want to draw attention to the dipole term, so this Q1, which is given by this term here. Again, we can ignore these last three terms. We'll notice that these terms here are given by spatial derivatives of quantities like the expansion near the observer and the shear as well. And so these spatial derivative terms we expect to dominate over the rest of the terms in this expansion. And so, as I said a few slides ago, we have many, many more independent degrees of freedom in this formalism. And so we can't use it on real data just yet in full, we don't have enough. And so what we now need to do is to make some reasonable assumptions to simplify this formalism a little bit, hopefully be able to actually use it for analysis. And so this is exactly what we wanted to do in this work. We wanted to calculate these parameters in full and identify which terms within these parameters are dominant to hopefully be able to ignore the ones that don't matter and constrain the ones that might be important. And so to do that, we calculated them in a realistic cosmological simulation. And because of the lovely generality of this formalism, we wanted to maintain that as much as possible in our simulations. And so for that reason, we use numerical relativity so that we can maintain these minimal assumptions on the metric tensor, although we do assume general relativity in this case. And so numerical relativity is a numerical method to solve Einstein's equations exactly without making assumptions on the physical qualities of the metric. And so this allows us to not make any assumptions about weak gravity, for example, or we don't need to assume that our geometry is flat locally or globally. And this is based on what we call a 3+1 split of our 4-dimensional space-time into our 3-dimensional space and 1-dimensional time components. We can see an example in this 3-dimensional space-time manifold M, where we've done a 2+1 split in this case, and we can split this into a series of 2-dimensional spatial surfaces and 1 dimension of time. And we can then project Einstein's equations into these spatial surfaces, and then that projection results in a series of evolution equations for the metric that describes these spatial surfaces. And so that allows us to specify some additional data and then just solve Einstein's equations to tell us how that data would evolve in full generality. And so this is a really widely used and very well tested method, which has been used for a couple of decades now successfully in many different simulations of relativistic phenomena. In particular, it's very important for the merger and emission of gravitational waves of binary black holes, and merger of neutron stars, supernova explosions, relativistic jets from accretion disks around black holes, and in the last 6 years or so, it's also been used for studies of inhomogeneous cosmology. And so there's a few groups working on this. I won't go into details about many others, but there's a lot of people very active in this field. I'll just say a few more words in particular about how we do this. So this is the work that I started during my PhD here at Monash. So we use the Einstein toolkit, which is a collection of modules based on the characteristic infrastructure. It's very widely used for simulations of binary black hole mergers and neutron stars. It's free and open source, and so we wanted to use this for cosmology. And so during my PhD, I wrote a module called FLRW solver to initialize realistic cosmological spacetimes, to then send this into the Einstein toolkit to be evolved with all of the really widely used modules to evolve the Einstein equations. And it's freely available at this repository, so do feel free to download it and do some simulations with it and email me if you're interested in anything else. So just a few things about the simulations themselves. We set our initial data using linear perturbation theory. Did I still hear anymore? Okay, good. So using linear perturbation theory, so we assume that the early universe is an FLRW with very small perturbations, which should be a good description based on our observations of the CMB. In particular, the initial perturbations are assumed to be Gaussian random, following the power spectrum of perturbations at the CMB. During the evolution itself, simulations we use right now are matter dominated. So this means we have no dark energy. And so we're not looking at a lambda CDM universe, we're just looking at a CDM universe. And the reason for this is just because the modules that we use were not built for cosmology. But this is an improvement that is currently in progress. My PhD student, Michael Williams at Canterbury, is working on adding in lambda to these simulations. And all the simulations I'll talk about are based on a continuous fluid approximation for the hydrodynamics. And so we don't have particles in these simulations. But this is something that is in progress and making very, very good progress. I learned this morning with Spencer under Daniel Paul. And so for this work in particular, the simulations don't quite look like this cosmic web you see on the left-hand side. Instead, we're really looking at a more large-scale universe. We're really looking at large-scale structures here. So this is a two-dimensional slice through the simulation at redshift 0 that we're looking at. It's up a lot worse on the projector than on the screen. But this whole simulation is 12.8 gigaparsec across. And so what this means is that we are explicitly not sampling any structure beneath 100 megaparsec. And this is to do with the assumptions that NASA had to make in deriving the formalism. I can go into more details if you like, but it's not super important. And so I just want to emphasize we're looking at a very smooth model universe here. And so now what we wanted to do was to place a set of observers within the simulation. And for each one of those observers, calculate these effective cosmological parameters in a fully general scenario and compare them to their FLRW counterparts and see how large some of these anisotropic effects may be. And so here it's just for one observer, for example. And so what we're looking at here is an all-sky map, a mole-wide projection of these effective cosmological parameters relative to their FLRW counterparts for just one observer in a simulation. And so if we're focusing on the Hubble parameter here, basically if we were looking at an FLRW universe, this would be totally uniform. And this kind of, in this case, quadrupolar variation as the observer looks on different directions in the sky. And so we can see a few % variation depending on where this observer looks. And if you think back to the quadrupole, the multipole expansion I showed you for the Hubble parameter, we only had a dipole and a quadrupole contribution. In particular, here we can see that the quadrupole is the dominant one there. So the effective deceleration parameter is shown here, which is dominated by dipole modulation, which is related to the spatial derivatives of expansion that I mentioned before. Effective curvature and jerk parameters here.
So Hayley, are you saying if you look at different units, you find that if you look at different places in the sky, you should find 4% variation
in this particular simulation? That's what and this particular observer in this particular location in this simulation sees.
That be ruled out.
Ruled out.
You know what the observed variation on the sky.
I mean, yeah, a bunch of different people looked into that and come to kind of different conclusions. But yeah, see, there's a few different ways to do that. You can either include this quadrupole variation in your constraint, or you can just, take supernovae from certain directions and constrain it separately. using
So,
FLRW.
for a 4% variation.
No, I think the error bars is still too big, but I can't think of the exact numbers. But I mean, there's a few caveats to this in the sense that this is a CDM universe, not lambda CDM. And so that means that our structures will be overall more dense than a lambda CDM universe, which will enhance these effects relative to a universe with lambda. And so you might expect this to be smaller. Qualitatively, you would still expect the same variation, that you would still have a quadrupole in a lambda CDM universe, but the amplitude would just be lower when you have lower density contrasts.
So Hayley, sorry, maybe just, that is the fact that this is just one observer looking at just as the reason why that Hubble constant never goes below 1.
Yes, exactly. So just this, for this particular observer in their environment, sometimes you see a kind of even plus or minus, and sometimes you see minus, sometimes you see plus. So as I said, this is just one observer. We've done this for 100 observers. We have a link to a Google Drive in the paper if you want to see this plot for 100 observers. But the point I want to make here is that every observer sees a totally different signature. So just putting it on the Hubble parameters, it's always a quadrupole dominating in this case, but the signature always looks different, and the amplitude variation is always different as well. But even just from kind of eyeballing this, we can see, as I said, we always have a quadrupole dominating the Hubble parameter. And even in the effective deceleration parameter, we mostly have this dipolar anisotropy dominating the signal. But we've also got kind of a mix of higher multipoles in there. Yep.
Can you comment on what's the effect of the fact that you don't actually resolve anything below 100 megapascals?
As in why we do it, or?
Yeah, why and like what effect that would have on the scale, like the differences between them.
Yeah, exactly. It's a really important point. And so the reason we do it is due to these regularity requirements of the series expansion. So in order to write down a Taylor series of the luminosity distance as a function of redshift, we need it to be a monotonic function. And so that then boils down to not being able to have collapsing structures. And so our universe needs to be expanding everywhere, because you can think as soon as we have a structure that's collapsing, that's going to blue shift our photon and affect the kind of the distance is not going to be monotonic anymore. So we need to, if we're going to be calculating the parameters in the way that we are in this work, we need our universe to be smooth and expanding everywhere. And so one way to do that is to just explicitly remove all small scale structure, which is kind of the crudest way to do it. And it's the way that we decided to do it in this work. There are maybe other ways, which we're now looking into now, and might potentially do some kind of smoothing of your universe, but that is very complicated when you're considering full GR. But you're totally right that once we have small scale structure, these will look totally different. And so that's also something that we're looking into now, is when you, so obviously in the real universe, we do have structure beneath 100 megaparsec. And so that small scale structure may impact your structures on 100 megaparsec. You can't necessarily just totally exclude that small scale dominating structure. And so that's also something we're looking into now, is if you consider a simulation which has a lot of small scale structure, and then look at these kind of large scale effects, do they look the same if you just totally neglected it? So that's something that's in progress too. And so what we might be interested in doing is looking at how much each of these parameters vary across the sky for each of our observers. And so to do that, we calculated this quantity delta, which we call the maximum sky deviation, which is very simply just the maximum value of a parameter minus the minimum across an observer's sky. And this gives us an idea of, well, how the maximum of how much each of these parameters vary from point to point. And so each of these panels is showing one of the effective parameters, normalized by our EDS value again, as a function of the density contrast at the observer's location. So each one of these points is showing this quantity measured for a separate observer at a separate location. And the point I wanted you to take away from this was that this line here, sorry, is the average over all observers. So what we can say is that typically our observers measure a 7% variance, maximal variance in the Hubble parameter across their sky. Yeah, so the value of the Hubble parameter on typically is 7% different depending on which direction these observers look. But it can be as high as 10% or as low as 2%. These other parameters, we see a much larger variation, so a few 100% for the deceleration parameter and much more for curvature and jerk. But these do appear at higher order in our series expansion. And so these variations will be suppressed at low redshift. The important point I want you to take away from this is that this anisotropy does not depend on the local density at the observer. So what I mean by that is you don't see a correlation with this sky variation and the density of the observer. We kind of have these blobs instead. And so what that means is that our observer can be sitting in a perfectly uniform, well not uniform, but not necessarily in a giant void or in a giant overdensity, and they can still have this up to 10% variation in these parameters in different directions across their sky. And so another thing we're interested in looking at, as I mentioned before, when we look across this, this breadth of observers, we don't always have a clear dipole like this one, for example, dominating the signal. We have some higher order multipoles mixed in there as well. And so what we're interested in doing is really identifying which multipoles dominated these parameters for the bulk of our observers. And for that case, we've had a Part 3 student at Cambridge, Jess Powell, who's been working on this over the last 6 months or so. And so her job was to take these sky maps for our set of 100 observers and take the angular power spectrum and identify which of these multipoles are dominant across our set of observers. And so these are some of her really nice violin plots here, where what she's calculated is this ratio R, which is giving us the ratio of a given multipole relative to the monopole. And so I'll talk through this a little bit more as well. This is the effective Hubble parameter. So here with L equals 1, we're looking at the dipole contribution to the effective Hubble parameter for our set of observers, where this mole gene is telling us that most observers are seeing that value. And so this is obviously very suppressed with respect to the quadrupole contribution to our effective Hubble parameter. And so from this, we can say that for most of our observers, the quadrupole is around 0.1% size of the monopole of the Hubble effective Hubble parameter. And I'll just show the effective deceleration parameter next, where again, we're looking at L equals 4. And from this, we can just kind of eyeball it and say, well, our dipole is the dominant contribution for all of our observers. And in particular, this dipole can be up to 50% the size of the monopole of the deceleration parameter. And one thing that we weren't really expecting was that this, the octopole is quite large and is about 0.1% as well for all of our observers. And so this work was really important in, instead of just roughly eyeballing all of these maps, we can really say for each specific parameter, which multipoles contain dominant contribution for all of our observers, and that can then allow us to safely neglect some of these terms which we know are subdominant in this multipole expansion. And so that's basically what I just said. And so this will then allows us to actually use this general cosmographic formalism to try and constrain some of these anisotropies in our data. And so that's exactly what we did in this recent paper here, led by Suhail Devon, who I should have mentioned was co-supervising Jess's project. So do check out this paper if you're interested. And this is something that Jess is now working on. It's improving these constraints using new supernova data. Spoiler alert is we can't find them yet. That's what you're wondering. But hopefully with this new exciting plus supernova data, we might be able to rule something out or detect something. Okay, great. So this particular, how much time do I have left? Oh, okay. So writing down this kind of cosmographic representation as a Taylor series in redshift is only valid while our redshift is small. Because as soon as we go to high redshift, our higher order terms will dominate and our series will diverge. Usually this cosmographic representation for FLRW is used for redshifts less than 1. But what we found in this paper is that truncating this series at third order in redshift, while including the effects of inhomogeneity and anisotropy, may not be a good representation of the luminosity distance. And the reason for this is if you think of an inhomogeneous universe full of structure, instead of the FLRW case having a very smooth distance redshift line, we're instead going to have a line which varies depending on the environment in the universe, whether it's expanding or collapsing. And so in order to capture the wiggles in this luminosity distance redshift line, we're going to need a very high order polynomial. And in particular, in Appendix A of our paper, Asta gave a really rough order of magnitude estimate that in order to correctly approximate the true luminosity distance to within 1% out to a redshift of 0.15, so not very high redshift, we may need to include up to 8th order terms in this series expansion. So the 3rd order truncation is really probably not enough when we're considering homogeneity. And so this is just a very, very rough order of magnitude estimate in order to gain a better understanding of the regime of validity of this cosmographic representation. One thing that we can do is use ray tracing in full GR. And so this can allow us to both study the validity of this series expansion while also just learning about anisotropies at all redshifts and not being constrained by the approximations in this series. And so I'll just spend a few minutes going over what I mean by this. So ray tracing is really just what it sounds like. It's really tracing the path of light rays through a particular spacetime. And you might be interested in doing this in our simulations and our numerical relativity simulations. And what this involves is solving the geodesic equation, which is describing the evolution of the photon form momentum KU. And so this gives us the energy of the photon as it traverses through the spacetime along its geodesic. What we also need to calculate distances is to evolve a small bundle of light rays in the spacetime. So the reason for that is we don't, when we're observing something like galaxies, we're observing an extended source. And so what we need to do is track a small bundle of light rays and how that ray is kind of squeezed and expanded as it moves through the spacetime towards our telescopes. And this will allow us to calculate distances to faraway objects. Okay, and so the first application of this ray tracing that I've done is exactly to assess the validity of this cosmographic representation. And so just looking back to this series expansion, which I showed before, in this previous paper I've been talking about, we calculated these individual cosmological parameters within the simulation. And so now, in order to look at the luminosity distance itself, we just need to substitute those parameters back into the series expansion to give us luminosity distance at a particular redshift. And so that is shown in these maps down here, again, just for one observer at 3 different redshifts of 0.03, 0.07, and 0.1. And so now the idea is to take the same simulations and the same observers and use these ray tracing techniques to calculate the exact luminosity distance for that same observer for each same line of sight. And then we can make a direct comparison and see how good this cosmographic approximation is and at what redshift it starts to break down. And so at the top here, I'm showing 3 maps for the same observer in the same simulation using ray tracing. So this is really the exact luminosity distance for that observer, and this is the approximate one. The point I want you to take away from this is that it does a pretty good job at low redshift. It does an okay job at medium redshift, but we can start to see it really overestimates the anisotropies at a redshift of 0.1. And so using this kind of comparison, we can make a more concrete statement about within what regimes this cosmographic approximation is valid. And I'll end on this slide. But so we can actually quantify this difference by comparing the luminosity distance at each point on this map and calculating the L1 difference across the sky for a set of, here I think it's 100 observers. And so here we're looking at the L1 difference, which is given up here between the ray trace luminosity distance and the cosmographic approximation shown by these blue points, and the ray trace luminosity distance versus the FLRW distance, which is shown by these red points. Again, as a function of the observer's local density for 3 different redshifts here. So again, the point I want you to take away from this is a 1% difference. This cosmography gives us a better than 1% prediction of the luminosity distance out to redshift of 0.1, which is actually a lot better than what we expected based on this work with Asta I've been talking about. But this is a very smooth model universe, and you'll notice that the FLRW distance is also correct to about 1% at all of these redshifts. And so we're really looking at very small variations, but for low redshift, this cosmography does about an order of magnitude better. And so this is leading into the question that Nikhil asked, is that what we now want to look into is what happens when we add small scale structure into the equation. I think I'm going to run out of time. I'd rather have more time for questions. And so I'll just skip through this and just conclude in that when we're looking at this cosmographic representation of the luminosity distance, we saw the coefficients generalized in non-trivial ways when we include the effects of homogeneity and anisotropy. And so we looked at these anisotropic variations across the observer's skies, and this could impact, for example, surveys which don't have a complete sky coverage. And so if we're just looking, pointing our telescopes in a particular region of the sky, we may infer these parameters to be larger than the actual monopole contributions based on these anisotropic variations. And now we're moving on to assessing the regime of validity of this cosmographic approximation using ray tracing. And this ray tracing is also useful for a range of different stuff, in quantifying general relativistic effects on observables, and also studying these anisotropic effects free of these approximations. So yeah, I'll end it there. Thank you.
Very much. Any questions?
Thanks for doing this, Hayley. So on the subject of sort of expanding your description by including them in more terms in your Taylor series and so on, I guess the question is, what is the ultimate goal, right? Because the goal, of course, is to accurately describe the structure along every line of sight. I understand that you need lots of terms, and one can ask whether the Taylor series is the right best way to do it, or whether you want some different representation at some point, etc. But
yeah.
but if the goal is to sort of say, okay, well, what's the large underlying picture, and there are some inhomogeneities, and maybe some description of the inhomogeneities in terms of their typical scale, size distribution, etc. Right? Could there be an alternative sort of statistical description rather than a description along individual lines of sight that would be more relevant?
Yeah, possibly. So you can use, if you have a survey that, say, perfectly samples your whole sky, and you can resolve these multiple features, for example, the quadrupole in this Hubble parameter, then you can learn something about the local shear in the universe. And you're totally right that when you have a, can I draw? If you look at like all of the structure, if we look at our observations, like the supernova plot looks something like this, right? And so usually we fit an FLRW line, which just looks like that. If we wanted to, for example, fit this full formalism, that's essentially fitting a line like this, right? It's describing all of the structure and all of the fluctuations. We can't really do that because we don't have, there's too many degrees of freedom. So what we might be able to do instead is kind of fit something that looks like this and just include kind of our large scale fluctuations like the quadrupole in the Hubble parameter, for example. And so this is something that we're working on, Asta and I are working on now with some others, in how do we smooth our data to arrive at this kind of, this smoother modulation. It's not so straightforward. But that's essentially what we're gonna have to do, something like that to be able to quantify the kind of more larger scale.
Right. I guess what I was thinking of is, rather than trying to fit this, right, whether it would make sense to say, okay, here is the overall trend, right? That's a simple thing. And then I have a statistical description of the, let's say, the typical size of the fluctuations and the typical, scale of the fluctuations. Like, am I fluctuating by 1% or 5%? Am I fluctuating over scales of, by the time I change redshift by 0.01, or by the time I change redshift by 0.1, what's sort of the typical size this way, typical size this way, etc. And then if I have a statistical description, right, that's kind of all I really want to know.
Yeah, sure. I mean, yeah, in theory, and that's what simulations will be useful for, right? Because then you have both you know exactly what the shear is near the observer, and you can also see what the scatter is. And so that's kind of stuff that I'm interested in looking at now with the ray tracer. Yeah.
Just to follow up on the same point. So if I understand what you're suggesting, you're saying that the scatter in this plot is real, and not just, well, I mean, it could just be real and not just statistical errors.
Well, there is, you know, we always, this scatter is always something to do with just sure statistical errors, but also with like local motions.
You're saying that there's a prediction about what the real scatter should be constructed like this.
Yeah, in theory. Yeah, I mean, it's I don't know the details of how to do it. But
So effectively predicts the error bar as a function of which.
maybe, yeah.
Isn't it a little bit more that if you extend that plot to not just being one dimension, Z, but also sky, you've got RA and deck and sky, and at least broadly you've got that divided up into dipole and quadrupole. You've only really got a couple of extra degrees of freedom in terms of the axes on which dipole and quadrupoles are defined. And then you're talking about doing the fit in that space rather than
So you can do that. Yeah, exactly. Yeah. So that's exactly what we did in the paper I said earlier. Is you really write down your like Hubble parameter as like a H naught plus a quadrupole term, which has introduces some additional parameters like the axis and the amplitude, and all the, in the case of the quadrupole, the eigenvalues and the direction. And then you constrain those directions using adding the direction of the supernovae into the fit. Because in an isotropic analysis, this is the kind of thing you would do. This is just a very rough picture that I like to draw to describe it, but yeah, you're exactly right. So that's what we did in this paper, is constrain a quadrupole in H and then the dipole in the deceleration parameter as well. Yeah, I know. I mean, at the moment in the constraints we did here, I think there's, oh God, something like order 200 maybe. But in like the recent transit surveys are kind of getting 1,000, order 1,000. So it's a pretty big increase. So NP plus is the one that's just been released, which has a lot more supernovae. So hopefully that'll give us more constraining power to resolve it.
I assume there's some down solution, right? Because you can't use any type of linear, like it has to be a very clean, pristine type. Like because there's potential lensing or potential sort of dust artifacts.
Yeah, so there's so Suhail one is the supernova guy who we've recruited to help us with this. So there was a lot of like corrections and assumptions that go into things like the evolution of supernovae, dust extinction, and all that kind of stuff, which I don't really know the details of. But yeah, these fits are all done like after that kind of stuff. It's the astrophysics is being dealt with.
So yeah, I think you mentioned something like 61 parameters.
Yeah.
I mean, that's going out to like third order in some small redshift.
Yeah.
So I mean, can't you just fit the data kind of smaller redshifts and go to second order initially?
Yeah, exactly. Yeah, exactly. So that's one option, and that's kind of exactly what we did in this work, is reducing the degrees of freedom by saying we know that the quadrupole is dominant in H and the dipole is dominant in Q, and then you can neglect a ton of those degrees of freedom. But you're talking about like fitting it in full, but only in second order. Yeah, for sure. And I mean, for example, first order, this is basically all you have is just a monopole plus this quadrupole. And so you could do this essentially a full first order fit if you just look at really low redshift. I'm not sure exactly how many second order introduces, but it would still be a lot. Yeah.
I guess just one question. So the homogeneities that are sourcing these departures from isotropy homogeneous expansion. I mean, those are also reflected in multiple large scale structure. Right? So could you imagine doing like a joint fit for these parameters and also to like large scale structure data?
Yeah, I mean, maybe I don't really know the details of that, but yeah, I guess so.
put you on the spot. So you sort of hinted that like there's some things in there which would give you acceleration to the parent. What you're getting extra ingredient, perhaps due to some weighted average things, or so is that would that manifest as like a quadrupole thing? Is it plausible? Is there any mileage in that that's not just a local void thing?
Well, yeah, so this is different to the local void arguments.
Yeah.
And so the negative Q, I mean, again, this is just for really low redshift stuff, right? And we have benefits from high redshift stuff as well. So I don't think this is going to solve dark energy. But the point is just that it's not necessarily obvious that your Q has to be positive if you don't have accelerating space-time. And what we showed in this paper, which I think I have in here. So another thing you can look at, instead of looking at like the variation across the sky, is you can take an average across each observed sky and essentially look at the monopole contribution or the isotropic contribution to those parameters. And so looking at a set of observers for the deceleration parameter relative to the FLRW, when we consider a full sky average, so taking all directions of the sky, you get kind of this like plus or minus 40% variation. And this is kind of like the local void effect. So depending on the observer's local density, they will have kind of a higher or lower deceleration parameter. And then what we found is when you cut the sky in half and don't fairly sample your sky, so you only look at preferentially one direction, then that's when this parameter can really blow up, and you can start to see negative deceleration parameters even though there's no lambda in this simulation. But that is really just a result of this large dipole in the deceleration parameter, which is when you cut the sky in half, it makes a drastic difference to the parameter that you measure.
Right. So you're saying that you should any anisotropic contribution to these like terms should be seen as a map on the sky. Should be some variation in the sky.
Yeah, exactly. And we can maybe understand that again by looking at doing this all sky average. We're essentially looking at the monopole, so we're cutting out these sky variant ones. And so we're essentially looking at like these two terms are very small. So we're looking at this d theta dt, and we have this additional term, but this is a sigma squared. It's very small. And so we would expect this term to dominate when you do this kind of all sky average. The point is that when you don't fairly sample your whole sky, that's when these kind of additional terms could be important as well.
Okay, one last call for questions from Zoom. Okay, so yeah, we kind of out of time. So thank you very much for this exciting.
Thank you.
Just to note that we have another seminar on Thursday this week. Yeah, it's from 11 a.m. Also in Heinesen.
On Thursday in person or on the
Oh, hi.
in person? The speaker is Going on.
Thanks. Yeah.
Okay.